When we're talking about mechanical energy, we're talking about the ability to generate motion or to transform an object. So when we're talking about mechanical energy, we're invariably talking about kinetic energy. Okay, so kinetic energy is often, well, it's basically referred to as the motion of an object. So kinetic means movement. It means motion. In addition to kinetic energy, we also talk about potential energy, okay? And that's going to depend on an object's position within its environment. So when we look at these two types of energies, and we're going to break down, as we move through the idea of mechanical energy, we're going to break down kinetic energy and gravitational potential energy. We're also going to look at something called the Work Energy Theorem. So let's first start with the idea of kinetic energy. So kinetic energy, okay, is referred to as the energy of movement. So if we want to think about movement, movement brings in the idea of kinematics. Okay, it brings about the rate of movement. And in order to play around with movement, there's two variables that come into play here. One is the mass of the object, and the other is the rate at which the object displaces, or its velocity. So we say that kinetic energy, all right, so energy kinetic is going to be equal to 1/2 the mass of the object times its velocity squared. And this kind of makes sense because if we talk about kinetic energy as being movement energy, then it makes sense that we're relying on a velocity here. Because if you are not moving, then you have no kinetic energy. You also have no velocity. From this equation, we can also see that the mass of the object is going to be directly proportional to the amount of kinetic energy. So the greater an object's mass, the more kinetic energy it's going to have. So if we look at the example here to figure out the kinetic energy of a 1,200 kilogram car traveling at 100 kilometers per hour. The first thing your eyes should see is this kilometers per hour. Kilometers per hour is not the same as meters per second. So that implies that you have to make the conversion. So we're going to work that out, and then we're going to plug it into the actual formula. So working that out, I end up with 27.78 meters per second. Now I'm going to input this into my formula. So we've got EK is going to be equal to 1/2 m times v squared. So if I'm trying to figure out what all this is, I'm just going to input my stuff here, and that's going to give me 1,200 kg times my velocity, which is 27.78 meters per second. This is squared, and all this is going to be divided by 2 from that half out front. So this is going to give me a pretty big number, okay, that I'm actually going to break down scientific notation. So 63 times 10 to the 5. Now, remember, energy is measured in joules, right? And we've talked about how we go from meters and kilograms and seconds all the way to joules. So we've got our kinetic energy here. Now, once we have an idea of what kinetic energy is, we can then make our way into the work energy theorem. If we remember from the previous chapter, we talked about the relationship between work and the resultant force required to carry out that work over a certain displacement. Okay, so if we remember, work total we remember that it was equal to the resultant force times the distance traveled times the cos of the angle between these two. Okay, so if we're talking about maximum work, then the angle there would be 0 degrees. All right, the force being applied would be totally parallel to the horizontal surface. We'd be getting maximum work. Now, the work energy theorem tells us that work total is also, or it can also be defined by the difference of the final kinetic energy versus the initial kinetic energy. So in other words, the change in kinetic energy in two different instances. So it tells us that we can have delta EK here, which is the same thing as saying EK final minus EK initial. So we've seen this before. We've seen how you can actually figure out a certain variable more than one way. And that actually helps us out because there's not, when we look at actual problems, we see that there's not always every variable that we want or need to solve something. And it's better to have more than one way to solve. So if we look at this, we've seen something like this before when we actually talked about our forces and our dynamics unit, where we talked about the fact that your resultant force is equal to the sum of all forces. And we actually find out that when we're looking at Newton's second law, the same thing happens here where something else can be used to actually find the resultant or net force. And that's that it's also equal to the mass of the object times its acceleration. So this is just another example of having more than one way to actually solve for a variable. And if we want to actually break down where we go from this right here to this, we can look, or we're going to look at how that actually happens. So let's look at that original formula. Now, you'll notice that I've actually replaced my delta S with a delta X, because if we're talking about horizontal displacement here, I'm going to be talking about displacement in my X, which is what we've actually looked at all year. And I'm going to assume that I've got maximum work being done here. So I'm going to assume that the angle between these two, okay, between the force and the displacement is 0 degrees. And if you cos this, that's the same thing as saying 1. Okay, the cos of 0 is 1. So now let's play around with this formula. Let's start inputting all of the things we know about this formula. So we know that this guy right here, okay, the resultant force is akin to saying that it's also MA, right? So we also know that according to Newton's second law, I can replace my resultant force here for the MA. So let's change this equation up now. So we're now up to work total is going to be equal to the mass of the object times its acceleration times the displacement. And I'm not even going to throw the 1 in there anymore because we know it's there. Okay? So we're good so far. Now, we don't have an acceleration, but we know that acceleration is nothing more than the relationship between the change in velocity. So if I actually import, let's say, I'm thinking about any of the formulas that have both of my actual velocities in them. Okay, so that equals to equation 1, equation 2, and equation 4 from our kinematic equations. I don't want to have to deal with additional variables here. So I'm going to actually remove equations 1 and 2 because they both have time in them. Equation 4 is the only equation that has only the change in velocity, acceleration, and displacement. These are the things I'm looking for. So if I take this now, and if we remember, equation 4 is v final squared equal to v initial squared times 2 acceleration, times 2a delta x. So there's my equation 4. Now, if I want to replace my a here, okay, because this is the only variable right here that can be found in this equation, I can actually rearrange this equation to actually solve for a. So we're playing a kind of a substitution game here. So that means if I want to isolate my a, I'm going to bring this guy over. So we end up having v final squared minus v initial squared is going to be equal to 2a delta x. And I can actually isolate my a here by dividing both sides by 2 delta x. So by doing that, I'm isolating my a. So now I have something that I can sub into my work total equation. So let's go back to our equation here, and we've got our actual work total, which is going to be equal to what was our force, so MA, right, times delta x. Now, if I want to sub this variable in for my a, I end up having my m, which was there, and I'm going to take my kinematic equation here and input it. So you should be starting to see what's going to happen here. You should be starting to see some of those elements of the kinetic energy formulas, because we know full well that these x's are actually going to cancel out here. All right, we're going to end up getting rid of those, and that's going to bring us to the idea that this variable here is going to be multiplied by the m, and this variable here is going to be multiplied by the m. The 2, or the 1/2, is shared by both. Okay, so this is where we actually get the idea that work total is going to be equal to 1/2 m v final squared minus, because that's where that guy comes in, 1/2 m, because m is being multiplied by both of these variables, so it has to show up in both places, v initial squared. So this is where we actually get that relationship between both of those equations. So we're going to actually do a couple examples. So the first example we're going to look at is just a simple figure out the kinetic energies. Okay, so if we work through this, we can actually find the initial kinetic energy using the EKI formula. We can then find the final kinetic energy using the EKF formula, and then we can just subtract them to get our work total. So I'm going to let you actually work this out for a bit, and I'm going to then input some variables. So if you want to pause it now and work through it, I'm going to put the answer key up in a second. So if we look at this, we can see that because it's at rest, automatically that tells us there's no initial kinetic energy. We can solve for the final kinetic energy, and it's simply the difference between the two. The next example of a problem that we're going to carry out is a slightly bigger one, and it involves us actually figuring out the work done by different forces. If we go back to the idea of free body diagrams, we see that there's a lot of different ways you can solve this. And I'm actually going to cut this video here, and I'm going to make another video of the actual example for the work energy theorem involving the breakdown of the different forces.